Good morning, students. Thank you very much, students, for clicking on my video. I'm your Nagini ma'am, chemistry mentor. In today's section, I'm going to discuss about the best trick to understand Ellingham diagram, students. Okay, this topic is from General Principles and Processes of Isolation of Elements, 12th class, Nana. So, what is an Ellingham, students? Ellingham diagram. In Ellingham diagram, Ellingham means it is a scientist name, students. Ellingham is the scientist name. He gave the graphical representation of he gave the graphical representation of graphical representation of Gibbs energy change versus temperature. Okay, Gibbs energy change versus temperature, students. So he gave the graphical representation, students. So that is the Gibbs energy change versus temperature. And what is the versus temperature? That means Gibbs energy change is nothing but delta G naught F versus temperature. Clear? So he gave the relation between delta GF naught versus temperature, students. Graphical representation he given. Okay, nama, graphical representation delta GF naught versus temperature. So main Ellingham diagram, it is used to find the best reducing agent, students. So what is the main use, students? Ellingham diagram. So Ellingham diagram, it is used to find the best reducing agent. Best reducing agent. Clear, students? It is used to find the best reducing agent. So first of all, I'm going to take one thermodynamic relation, students, in the first year. Thermodynamics, from the first year thermodynamics lesson. Thermodynamic relation, delta G naught is equal to delta G naught is equal to delta H naught minus T into delta S naught, minus T into delta S naught. What is delta G naught, students? Gibbs energy change. Okay, na? So what is G naught? Gibbs, standard Gibbs free energy change, standard enthalpy change, standard entropy change. Are you clear? So here delta G naught, it is used to check the spontaneity of the reaction, students. So what is delta G naught, students? It is used to check the spontaneity spontaneity of the reaction. Are you clear? That means whether the reaction is possible or not. Whether a reaction is possible or not. Understanding, students, it is used to check the spontaneity of the reaction. Okay, it does not predict the speed of the reaction, students. Are you clear? It does not predict the rate of the reaction. Only it is indicates the whether a reaction is possible or not. Whether the reaction is possible or not. Understanding, students? So that means that the reaction is spontaneous or a non-spontaneous reaction. That means here, see, students, some reactions will take place on its own. Some chemical reactions, those are calling as spontaneous reactions. Some reactions will not take place on its own, students. Okay, now with that reactions will take place with the help of external force. That chemical reactions are calling as non-spontaneous reactions. So what is spontaneous and non-spontaneous reactions, students? The reactions which takes place on its own, those are called spontaneous reactions. The reactions which does not takes place on its own, that means the reactions those are which takes place with the help of external force, those are calling as non-spontaneous reactions, students. Are you clear? Spontaneous, non-spontaneous reactions. Understanding, Amma? What is spontaneous reaction, students? Spontaneous reactions. So what is spontaneous reactions, Nana? Spontaneous reactions, the reactions which takes place on its own, on its own. What is non-spontaneous reaction? Non-spontaneous reactions. What is non-spontaneous reactions, students? The reactions which takes place with the help of with the help of external force. Are you clear? With the help of external force, students. So some reactions are taking place with the help of external force. Those are non-spontaneous reactions. Understanding? So delta G naught is used to check the spontaneity of the reaction, students. Spontaneity of the reaction. Okay, now see, students, here delta G naught is equal to 0. I'm taking delta G naught equal to 0. So here spontaneity, here how to say, students, delta, if delta G naught equal to 0, and next one, delta G naught value less than 0, this is delta G naught value greater than 0. So like this, in three ways dividing, students, delta G naught value, spontaneity of the reaction. If delta G naught equal to 0, the reaction is at the equilibrium. So what, students? The reaction is at equilibrium. Understanding? Equilibrium. Okay, if delta G naught less than 0, that means delta G naught value, what, students? Negative. Less than 0 means negative. That means the reaction is spontaneous reaction. The reaction is spontaneous reaction, students. Now coming to delta G naught greater than 0, that means delta G naught value positive value. Correct? Greater than 0 is nothing but positive value. That means the reaction is which reaction? Non-spontaneous reaction. Are you clear? Non-spontaneous reaction, students. Clear this one? Non-spontaneous reaction. Understanding, Nana? Now I'm taking one example, student. See, students, here. So here M element combined with oxygen produces here MO compound, Nana. Okay, now. So I'm taking this example, students. See here. Here I am taking graph. The graph is drawn between delta G naught F versus temperature, students. Okay, now. So here graph, if you take like this, see, students, this is delta G value equal to delta G naught value is equal to 0, Nana. Delta G naught equal to 0, and here this line graph you will get here like this, students, like this. Okay, Nama. So M plus O2 gives rise to MO, this compound. Here this reaction line, if you take graph, you will get like this, students. Understanding? So in the next example, in the next, Nana, I will take three examples, students. That means carbon undergoes three different oxidations, Nana. Okay, so there you can understand, students. So just I'm discussing here, the reaction is spontaneous, whether the reaction is possible or not, I'm discussing, students. M plus O2 gives rise to MO. Just I'm not balancing, just reaction. So this is the reaction, students. M plus O2 gives rise to MO. This is the first part, students. This is the first part. This is the second part. That means below this line, delta G naught equal to 0. That means the reaction is at equilibrium. Before equilibrium, after equilibrium, students. This is the reaction. So delta G naught equal to 0. This one. This is delta G naught. What we have to take, delta G naught less than 0. Above this line, delta G naught value, it is greater than 0. Correct? This is the first part. This is the second part I am taking. From here to here, this is the first part. From here to here, this is second part I am taking. Are you clear? Less than 0 is nothing but what is delta G naught value, students? Delta G naught is equal to negative. Delta G naught greater than 0 means delta G naught value positive. Are you clear? Delta G naught value positive. Now see, students, I am taking the first part and second part. This line I am dividing into two parts. First, this is the first part. This is the second part. This is delta G naught equal to 0. Below this line less than 0. Above this line greater than 0. Clear? Now I am taking the first part, students. At first part, What is the reaction? M plus O2 gives rise to MO. Kada? So here, if delta G is equal to negative, so at first part means delta G naught value what given, students? Less than 0, correct? So that means delta G naught value, it is less than 0. Delta G naught less than 0. That means delta G naught value what we can take? Negative. Are you clear? Negative. So if delta G naught is negative, what is the reaction, students? Delta G naught is negative. The reaction is which reaction? Negative is there means? Negative means spontaneous reactions. Are you clear? So what is negative, students? Spontaneous reaction. Here I discuss in number. See here, delta G naught. Here see delta G naught equal to 0, the reaction is at equilibrium. If delta G naught less than 0, negative means spontaneous, positive means non-spontaneous reactions. Are you clear? So see here, this is delta G naught is equal to negative. Negative is nothing but the reaction is which one, students? Spontaneous reaction. Okay, so the reaction is which one? Spontaneous reaction. Okay, now I'm taking the reverse reaction, students. At first part only reverse reaction I'm taking. What is the reverse reaction? Reverse reaction, MO gives rise to M plus O2, correct? This reaction, it will become reverse, M plus O2. Then here these conditions will become reverse, students. It is less than 0 now, so that's why here what you will get? Delta G naught value, it is greater than 0. Here less than 0, here greater than 0, means delta G naught value positive. That means the reaction is which reaction? Non-spontaneous reaction. Are you clear? Non-spontaneous reaction, students. Understanding, no? It is a non-spontaneous reaction. This is the first part. Now I am taking the second part, students. At second part, now what is the reaction, students? M plus O2 gives rise to MO. At second part, delta G naught value what, students? Greater than 0. So that means delta G naught value, it is greater than 0. Greater than 0 is nothing but delta G naught value, positive value. Positive means the reaction is which reaction, students? Non-spontaneous reaction. Are you clear? So which reaction, students? Non-spontaneous reaction. Are you clear? Non-spontaneous reaction. Now I am taking the reverse reaction, students. Reverse reaction at the second part only. Reverse reaction I am taking. That means MO gives rise to M plus O2, nana. So here what about delta G naught value? Delta G naught value is less than 0. This is greater than 0. It is when it's reverse, when the reaction becomes reverse, delta G naught value also reversed, less than 0. That means delta G naught value negative. That means the reaction is which one, students? It is a spontaneous reaction. So it is a spontaneous reaction. Are you clear? Spontaneous reaction. So finally what we can say, students, here this is the temperature. Here I am taking temperature from here. So here from this one, this is the temperature T1. Okay now, so this is the temperature T1. This dot here, this one I am taking as temperature T1. Now we can say that below this temperature T1, below T1 temperature, what will happen? The reaction is spontaneous, and above T1 temperature, students, the reverse reaction is spontaneous. Are you clear? That means the reaction is possible. Understanding, students? Understanding, nana? So what you have to write? Before T1 temperature, before T1 temperature, M plus O2 gives rise to MO, students. It is which one reaction? It is spontaneous reaction. Are you clear? It is a spontaneous reaction. After above temperature, after above T1, okay, after above T1 temperature, reverse reaction. The reverse reaction is which one, students? Reverse reaction, this is only so before T1 temperature, this is reaction, the reaction is spontaneous. After above T1 temperature, the reverse reaction is spontaneous. Are you clear? So here the reaction is spontaneous, and here reverse reaction is spontaneous. Here this reaction is spontaneous. Are you clear? So that only. So about T1 temperature, MO gives rise to M plus O2. M plus O2, M plus O2. The reverse reaction is spontaneous. Understanding, Nana? So the reverse reaction is which one, students? It is a spontaneous reaction. Clear this one? Understanding, students? Now I'm taking the an example, students. That means at what conditions best reducing when reducing agent is used. Understanding in what are in which condition a best reducing agent is used. That the based on that one example I'm going to discuss, you students. See here, I'm taking the graph. See students, here one example I am taking one graph. The graph is drawn between delta GF naught versus temperature, students. This is the graph. Here three lines I am taking. Here first line is, this is Ag2O line. This is Ag2O silver oxide. This is HGO and this one is zinc oxide. Three lines I am taking, students. Ag2O, HGO and zinc oxide. Okay, now I am coming to the first one, Ag2O line graph. Ag2O. So if I take Ag2O, students, see here, Ag2O, by heating, what will happen, students? Ag2O, it dissociates into silver plus O2. Are you clear? So just I am taking, this is the first equation, second, third equations I am taking. This is the first one, this is the second one, this is the third one. So first one I am discussing, Ag2O gives rise to Ag plus O2. I am taking the second one, which one, students? HGO. So HGO dissociates by heating, it dissociates into Hg plus O2. Are you clear? Hg plus O2. But these two reactions takes place at low temperatures, correct? This takes place at low temperatures. That means the decomposition, for the decomposition of metallic oxides Ag2O, HGO, here low temperatures are favorable, students. Here low temperatures are enough. That means here this temperature is just I am taking this temperature is T1. This is T1 and this one is T2, students. But T3, this is T3, students. This is T3. Okay, zinc oxide. Now from this graph we can say that for these two metallic oxides, for the decomposition, low temperatures are required, T1, T2. But for the decomposition of zinc oxide, students, it requires more temperature. Are you clear? Here at low temperatures only decomposition taking place. Now I am taking the third equation, students. Zinc oxide. Zinc oxide, by heating, it dissociates into Zn plus O2. So for this reaction, high temperature is required. Are you clear? So here temperature is T1, T2, T1, T2, this one, and this temperature is T3, students. So that means high temperatures are required. High temperature is required, students. Clear this one? Okay, now high temperature is required. So that means any chemical reaction requires more temperature to get the metal, students. So that reaction is costlier. So that's why to prevent that, that means to reduce the to reduce that effect, instead of heating to get the metal zinc, students. So that's why you are using reducing agent, students. Understanding, instead of heating you are using reducing agent. Are you clear? So any chemical reaction, students, requires more temperature for the decomposition. That reaction is very costlier. Understanding, students? So that's why this reaction is, the reaction is costlier. Are you clear? The reaction is costlier, students. Okay, Nama, it is very cost. So that's why to prevent this, the reaction is very cost. To prevent this, here instead of heating, to prevent this effect, instead of heating, reducing agent is used. Are you clear? Reducing agent is used, students. Okay, na? So reducing agent is used. What is the reducing agent, students? Here we are using coke. Okay, now that is nothing but carbon. So carbon is acting as a reducing agent, students. So that's a whenever zinc oxide, when we added carbon coke, then carbon can reduce the zinc oxide into zinc, students. Zinc plus CO. Are you clear? Zinc plus CO, students. So this is about the example, students. So here different metallic oxides. Are you clear, students? Now Ellingham diagram, students, it is used to find the best reducing agent. Correct? Before going to the Ellingham diagram, students, first I will discuss one example, students. One example, Lana. See here, students. So here I am taking graph, Nana. Delta GF naught versus temperature. Here I'm taking three, that means the carbon undergoes three different types of oxidation, students. I'm taking here, one is like this, next one, this one. So what are the lines, students? These are, so first one is CO gives rise to CO2, CO gives rise to CO2, C gives rise to CO2, C gives rise to CO. These three lines, this one and this one, this one. Okay, now so this graphs now I'm going to discuss, students. So I'm giving the numbering. So first one is, what is the first part, students? See, this is the first part, first equation. This is second equation. This is the third equation. Now I'm going to discuss you, students. Now at the first part, students, at first part, students, so what we can say, C gives rise to CO is their reaction. First line, first equation, C gives rise to CO. Now how you will get CO, students? C combined with half moles of O2, then we'll get the CO. Are you clear? Produces CO. Understanding, students? Carbon, when it is reactive with half moles of O2, produces CO. It is a solid, students. It is a solid and it is a gas. It is also gas. So just you calculate delta N value, students. Delta N is nothing but delta N for gases, that is change in the number of moles, then the NP minus NR, students. So that means the number of moles of products minus number of moles of reactants. How many moles of products? 1 minus 1 by 2. Here this is solid now, so 1 minus 1 by 2. Then you will get 2 minus 1 by 2, students. 1 by 2 you will get. That means delta N value plus 1 by 2 we got. That means delta N is positive. Are you clear? That means then delta N equal to positive. That means we can say that delta N value increases. Understanding, Nana? Increases. So that means whenever positive we got, delta N increases. Whenever less negative means delta N, that is delta N value decreases, students. It is positive now, so that's why increase. If it is negative, decreases. Are you clear? So now say, students, here graph, if you see, now I'm taking the thermodynamic relation, students. Delta G naught is equal to delta H naught minus T into delta S naught. Now see, Nana, delta G naught is equal to delta H naught minus T into delta S naught. In this equation, students, whenever temperature is increased, we know that change in the number of moles, delta N value, what happened here? Increases, kada? So increases. So number of moles increases, what will happen? The degree of randomness also increases. That means number of moles less, degree of randomness less. That means entropy is less. What is an entropy, students? Degree of randomness. Okay, now so delta N value increases, so that means the number of moles are increases, students. This is a gas, that means randomness is more. Randomness more, that means delta S value is more. Are you clear? Delta N value increases, number of moles, what will happen? That means delta S value also increases, students. This is in the case of gases. Are you clear? In the case of gases, if I take solid, students, the particles are, those are arranged in the orderly arranged in the orderly arranged manner. So that's why here degree of randomness delta S is very less. Are you clear? And if I take gases, students, the particles, there is a little gap will be there, so that's why randomness is less. Are you clear? It is less here, very less. In the case of gases, degree of randomness is more, because gases molecules are moves freely. So that's why whenever number of moles increases, students, that means degree of randomness also increases. So that means whenever temperature increases, see students, here temperature increasing, temperature increases, delta S naught value, whenever temperature increases, the gas molecules velocity increases, that means degree of randomness increases, delta S naught value also increases. Are you clear? So both are increasing. So that means this value, total value, it is increasing. Are you clear? It is value, this value is increases. Are you clear, students? So this value, total value is increases. Okay, so total value increases, that means which value increases? Negative value increasing. Are you clear? So this negative value is more, and delta H naught value, that is change in the enthalpy, that is nothing but during the formation of bond energy is released, so that is negative. This is negative, students, this is negative, this value also negative, then you will get the total value negative delta G naught. Are you clear? So delta G naught value negative, students, it is negative, this value also it is more, it is negative, you will get delta G naught value negative. That means we can say that delta G naught value negative is nothing but the reaction is which one, students? Spontaneous. Okay now, and then we can say that negative is nothing but delta G naught value less than 0. Are you clear? It is less than 0, that means delta G naught value we can say that decreases. Are you clear? Delta G naught value decreases. Understanding, students? Delta G naught value decreases. So that means whenever temperature increases, students, temperature increases. Okay, so temperature increases, what will happen, students? Temperature increases, delta G naught value decreases. Are you clear? Temperature increases, that means temperature increases, then delta G naught value decreases for the first line. So that's why graph, if you see here, delta G F naught versus temperature graph, you got like this, decreases. Understanding? So this is the line C gives rise to CO, correct? So that is the graph, students. That means whenever temperature increasing, delta GF naught value decreases. So that's a graph you will get like this. Now I am taking the second equation, students. In the main equation, what is the second equation, students? What is the second equation? This one. So second one is this one. C gives rise to CO2. This is the first line completed. Now this is the second line. This is the third line. Now I am going to discuss second line. Now see, students, second part. Second part. At second part, what is the reaction, students? At second part, what is the reaction? C gives rise to CO2. C gives rise to CO2. How CO2 you will get? When carbon combined with oxygen produces CO2. This is solid, this is gas, this is gas. Now you calculate number of moles, students. Delta N value calculate. Delta N is equal to, delta N for gases is equal to number of moles of products minus number of moles of reactants. So products 1 here, 1 minus 1 is nothing but 0. That means delta N value 0. Delta N number of change, there is no change in the number of moles. That means the number of moles. That means delta S naught value 0. That means there is no change in the enthalpy. That means there is no degree of randomness. Number of moles is equal to 0. Delta S naught value equal to 0, and temperature also equal to 0. That means when temperature increases, delta N equal to 0, delta S naught equal to 0. That means delta G naught, GF naught value also 0. Are you clear? So that means whenever temperature increases, students, temperature increases, delta GF naught value equal to 0. So that's why second graph we got constant line. Understanding? This is delta GF naught, this is temperature. That's why we got graph like this. This is delta GF naught, this value equal to 0. It is constant. Understanding, students? That means the reaction is at the equilibrium state. That means Okay, now see students, I'm going to discuss you third part. What is the third part, students? Third part. So what is the third part, Nana? CO gives rise to CO2, correct? CO gives rise to CO2. Now how CO2 you will get when combined with the half moles of O2 produces CO2. It is a gas, it is also gas, it is also gas. Then delta N value for gases you calculate number of moles of products minus reactants, that means 1 minus of products number of moles 1. Here this is also gas, now 1 plus 1 by 2, then how much you will get? 1 minus of 3 by 2, then you will get minus 1 by 2. That means delta N value you got minus 1 by 2, students. Minus 1 by 2 is nothing but negative value. That means delta N value decreases. If it is positive, increase. If it is negative, now decreases. So that's a delta N value decreases. Now I am taking the relation delta G naught is equal to delta H naught minus T into delta S naught. Now whenever temperature is increases, students, here delta N value decreases kada. Delta N value decreases. That means delta S naught value also decreases. Are you clear? It is also decreases. Understanding? Number of moles decreases, delta S naught value also decreases. Delta S naught decreases means what, students? Delta S naught decreases means it is negative value. Okay, it is negative. So that means delta S naught value negative. Whenever temperature increases, delta S naught value negative. Negative, here front side negative is there. Negative minus into minus, positive value you will get. This is positive. Are you clear? This is positive. When compared to this, delta H naught value is less. So that's a finally we will get delta G naught value positive value. Understanding? This is positive because here already minus is there. Here minus into minus, positive value will get, and this is negative minus, but this value is more when compared to this, then finally you will get the positive value. Okay, so positive value we got. That means whenever temperature increases, students, temperature increases, okay, now delta G naught value also increases. Positive na increases. So that's why graph, if you see delta G F naught versus temperature graph nana increases. So that's why we'll get the graph like this. This is CO gives rise to CO2 graph. Understanding, students? So like this you have to find the delta N value decreases, then delta N is decreases, that is change in entropy decreases. That means here decreases means negative value. Negative minus positive. This is positive. This is negative. But this value is more than this one. That's why we'll get the positive. Positive means increases. So graph is whenever temperature increases, delta G naught value increases, students. Understanding? So here how to find the best reducing agent. Now see students, here one example I am discussing you. So here the graph is drawn between delta GF naught versus temperature, students. Here the graph they given nana like this given. This is the iron oxide, students. This is the iron oxide given, and this is CO gives rise to CO2. This is gives rise to CO given. Now which is the best reducing agent is asking, students. That means to dissociate iron oxide, which is the best reducing agent, either carbon or CO, carbon monoxide. And here temperature also given, students. This temperature where they meet three lines, that temperature they given 1073 Kelvin given temperature. Now tell me, students, before here which is the reducing agent. Now the question is below 1073 Kelvin, which is the best reducing agent. After 1073 Kelvin, which is the best reducing agent. Are you understanding? So how to find it, students? That means to FeO line, you see Nana, FeO line to this line, okay, na, to the metallic oxide line, which is the lowest part. That means these lines, these reactions lines which are present in the lower part of to this line, that is the reducing agent, students. Now see, this is the line below 1073 means this part below, before 1073. That means here to this line. Are you clear? So to this line, students, which is the lower part? which is the lower part of the line is there? This one. Are you clear? So to this line, this is the lower part. Are you clear? Below 1073. After 1073, this line below part arrow, this one. So that means this is C. Are you clear? Carbon is the reducing agent. Before 1073 Kelvin to this line, this which is lower, this one. That means CO is the best reducing agent. After 1073 Kelvin to this line, which is the lower part, carbon is there. So carbon is the reducing agent. Are you clear, students? Understanding? So here, right here, above 1073 Kelvin, students, 1073 Kelvin, C to CO line is below. Are you clear? C to CO line is below. Understanding? C to CO line is below. Okay, below. So that's why what we can say that, students, it reduces below. Which is the best reducing agent, students? Which is the lower part? Just you remember, students, which is the lower part in the diagram to the metallic oxide. That is the best reducing agent, students. Are you clear? So here you just write, students, note, okay, to the metallic oxide line, which is present in the lower part, of the diagram, is best reducing agent. Are you clear? So which is the best reducing agent, students? To the metallic oxide line, which is present in the lower part of the diagram, is the best reducing agent. So this is the metallic oxide line to this line, which is the lower, this one. And if I take after 1073, that means to this line, which is the lower part, this one. That means this. Are you clear? So C2CO line is below. Understanding, students? That means iron to iron oxide line is above. Are you clear? It is above. Hence, it reduces FeO to Fe. Understanding, students? So that's why, hence, carbon, which is the best reducing agent, carbon. So to this line, above 1073 I am taking. So to this line, carbon is the best reducing agent. Understanding? Hence, carbon reduces iron oxide to iron. Are you clear? Iron oxide to iron. Now tell me, students, below 1073 Kelvin. This is the second case. Below 1073 Kelvin, students. Below 1073 Kelvin. Now, which is the best reducing agent, students? CO is the best reducing agent. That means CO gives rise to CO2 is line, CO2 line is below. Are you clear? CO2 line, it is below. Understanding? And iron oxide line is above. Okay, na? So iron to iron oxide line is above. Understanding, students? Hence, which one is reducing agent? CO. CO reduces the iron oxide to iron. Understanding, students? Iron oxide to iron reduces. That means carbon is the reducing agent where above 1073 carbon is the reducing agent, and above 1000 before 1073 CO is the best reducing agent. Are you clear, students? CO is the best reducing agent. Understanding, Nana? CO is the best reducing agent. Clear, students? Right. Next one more example. See, students, here one more example 2. Now see here, I am taking the graph delta GF naught versus temperature, students. Here I am taking the 3 lines. One is C gives rise to CO2, like this as it is I am taking. Okay, this one is CO gives rise to CO2, C gives rise to CO, and one more line they given, students. Here one more line is like this. This is zinc oxide line given. So which is the best reducing agent is asking, carbon or CO? Which one is the best reducing agent is asking. Now see, students, to this line, which is the lower part, here I told you which is the lower part, to the metallic oxide line which is present in the lower part of the diagram, that is the best reducing agent. Okay, so that you have to remember. to this line, which is the lower part, students. This is the lower part first to this line. So that's why carbon is the best reducing agent. Are you clear, students? So which one is the best reducing agent? So carbon is the best reducing agent to reduce zinc oxide to zinc. Are you clear, students? Zinc oxide to zinc. Understanding to this zinc oxide line, which is the lower part, this is the first lower part. So carbon is the best reducing agent. Understanding, students? So this is the Ellingham diagram, students. So here we can by using Ellingham diagram we can find the best reducing agent. So like this we can answer the question, students. These are the two examples, previous year's questions, students. You can easily understand. Okay, so after I hope you like this video, students. If you like this video, please like, share, comment and subscribe my channel, students. Thank you very much, Nana.